So, we continue a series of videos in which we're looking at solutions to the CSEC AdMaths paper of 2024. And in this video, we'll be looking at question 4. Now, question 4 says, use the definition of the derivative as a limit to find f prime of x for the function f of x equals x squared minus 3. Now, how do we use the definition of the derivative as a limit to find f inverse of x? Now, this is how the derivative is defined. So we have some function f of x, right? And the derivative, let's call that dy by dx, is defined as such. The limits as say h approaches 0 of f of x plus h minus f of x all over h, right? So this is how the derivative dy by dx is typically defined. So for any function f of x, we can say that derivative, or we can say for any function y equals f of x. Let me be more specific. Where's my cursor? So for any function, say y equals f of x, the derivative dy by dx is defined in such a way such that it is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Now, let's try to explain this further with an illustration, right? With an illustration. Now, suppose we have a curve. Let me try to represent this graphically, right? So, suppose we have a curve, right? And let this be our curve y equals f of x. So this is our curve y equals f of x, right? Now let's say we have a point on the curve. Let's call a point A. And the coordinates of this point, of course, is given as x, f of x, right? So let's call that point A. So this point is A, and A has as coordinates the point, well, x, f of x. Now let there be another point B on the curve such that there is a small change in x given by h. So this point is B. And so if the change in x is the value h, then essentially the coordinates of this point would be x plus h, f of x plus h, right? So if you were to examine this, of course, then as I said, the change in the value of x would be h, because if this value here is x and this is x plus h, the change in the value of x would be h. Similarly, the change in the value of the function or the y value would be the difference between f of x plus h and f of x. Now, let's draw a chord which of course connects A to B, a straight line connecting A to B, and that of course will be a chord. What color should I use here? Let me use green. Supposed to be a straight line, right. So we managed to draw our chord, right? So let me just fix it up a little bit. Right, so there we have our chord. Now for our chord, we can say that the gradient of our chord AB, so the gradient of our chord AB is equal to the change in y over the change in x. Now this change in y is going to be given by f of x plus h minus f of x, because you know that at the point A, the y value is f of x. At the point B, the y value is f of x plus h. Now the change in x will now be x plus h minus x, right? So if we continue, what this tells us is that the gradient of the chord delta y over delta x would be equal to f of x plus h minus f of x all over, and now we will see that x plus h minus x would be equal to h. So let me just try to bring the graph down so it is very close to our thing here. Let me see if I could just copy this entire graph. Right, so Control C, put it here, Control V. Right, right, so there we have our graph, right? Now, what happens basically as the point B gets closer and closer to A? As the point B gets closer and closer to A, it means that our chord, as the point B gets closer and closer to A, then what this means is that, so let's say the point B comes here now, point B is here, and eventually it might get closer as well, might get a little bit closer. So what's going to eventually happen is that as it gets closer and closer to A, then essentially the chord becomes a tangent to the curve at A, right? So essentially, as the point B gets closer and closer to A, this straight line, the chord, eventually becomes a tangent to the curve at A, and this is how we basically tend to define the derivative. So we basically say that as h approaches 0, so we can say that as h approaches 0, then delta y over delta x approaches dy by dx. Or we can say that the change in y over the change in x essentially approximates to being the dy by dx, which of course is equal to the gradient function of the curve at A. Or we can say the gradient of the tangent to the curve at E. So the gradient of the tangent to the curve at E, right? And so essentially we will see that this definition of derivative dy by dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, right? Because essentially dy by dx, as I said, dy by dx is equal to the lim as h approaches 0, delta y over delta x. And therefore, that is what we get. So by definition, the derivative is equal to limit of f of x minus f of x plus h minus f of x over h as h approaches 0. Now, this question didn't really require the graphical explanation. It just basically required you to be able to use the definition of the limit to actually find the first derivative. And of course, this process is what we call differentiating from first principles. So this process of using the limit to find the derivative is what we call differentiation from first principles, right? And you can differentiate almost any function using it, but it gets more complicated as the function gets more complicated, all right? So let's really go and apply this now to the particular question. So this is what the derivative, or how the derivative is actually defined. So let's go back to this right here. What do I erase? What do I erase? Let me just make some space here. All right, so what we have so far is this. Now, we can basically say that f of x is equal to x squared minus 3. Now, what we need to find now is f of x plus h. So, f of x plus h. And how do we find that? We basically replace x in f of x with x plus h. And so this becomes x plus h squared minus 3. We expand the brackets, so this becomes x plus h times x plus h minus 3. And so this gives us x squared plus xh plus hx plus h squared minus 3. Of course, you know that multiplication is commutative, and so xh and hx are the same thing. And this therefore gives us x squared plus 2xh plus h squared minus 3. So that right there is f of x plus h. Um, f of x plus h. Now, by the definition of the derivative, from the definition of the derivative, we will see that dy by dx, right? So from the definition of the derivative, what do we see? We see that dy by dx is equal to lim as h approaches 0 of f of x plus h minus f of x all over h. Now let's work out the numerator part first. So let's work out f of x plus h minus f of x and see what that gives us, right? So f of x plus h minus f of x is equal to x squared plus 2hx plus 8 squared minus 3, and this now is going to subtract f of x, which of course is x squared minus 3. And so we have minus brackets x squared minus 3. So expanding the brackets, we get x squared plus 2hx plus 8 squared minus 3 minus x squared plus 3. And some cancellation will now take place. The x squared terms will cancel, and the 3's of course will cancel, and this leaves us with 2hx plus 8 squared. So therefore f of x plus h minus f of x is equal to 2hx plus 8 squared. So now we can apply the limit, and so we can say that dy by dx is equal to lim as h approaches 0 of f of x plus h minus f of x all over h. And so this gives us lim as h approaches 0. This is 2hx plus 8 squared all over h. So first of all, what we will do is we will simplify by dividing through by h. And so this gives us lim as h approaches 0 of, now 2hx divided by h, that gives us 2x, and 8 squared divided by h, that gives us plus h. So essentially, this simplifies to give the limit of 2x plus h as h approaches 0. Now, how do we evaluate this? What this is basically saying is that we want to find the value of 2x plus h as h gets increasingly small, very small, and approaches 0. So in other words then, as h gets very small and approaches 0, then this becomes 2x plus 0, which is simply equal to 2x. And therefore, what this tells us is that f prime of x is actually equal to 2x, right? So we've managed to find the derivative using the definition of the limit, or what we call differentiation from first principles, right? So f prime of x is equal to 2x. And of course, if we were to go back and apply the regular rules of differentiation, if we say, for instance, y equals x squared minus 3, then we see that dy by dx, so what do? We bring the power down, multiply by it, reduce the power by 1, and this being a constant term will differentiate to give us 0. So this, of course, is simply equal to 2x. And this is, of course, verification that what we did previously is correct, right? Now, there's a next part of the question which basically says, hence, determine the value of f double prime of 5. And so since we just worked out that it's f double prime? All right, f double, should that have been f double prime? Because the question says hence. I didn't copy the how many marks it was worth, but it says hence, determine the value of f double prime of 5. Now, let's do what the question actually asks us to do. So this is what we have. We have f prime of x is actually equal to 2x. If we were to find the second derivative, it means that f double prime of x would simply be equal to 2. And because f double prime of x is a constant term, it doesn't matter what value we substitute, we'd get that f double prime of 5 would still be equal to 2. But I'm inclined to believe that this is a typographical error, and what they want us to find is actually f prime of 5 as opposed to f double prime of 5. And so if that is the case, then f prime of 5 is simply equal to 2 times 5, which gives us 10, right? So in this particular case, if of course the error exists, which I think it does, then it means that f prime of 5 is equal to 2 times 5, which gives us 10. But if it was not an error, then of course we'd have to differentiate a second time to find the second derivative. And because f double prime of x equals 2, a constant, then it simply means that regardless of the value of x, f double prime of that value would simply be equal to 2. All right? So that was part A of the question. Now let's move on to part B. Now, part B of the question now says, given that y equals sine x over cos x, show that dy by dx equals 1 over cos squared x. Now, dy by dx, or rather, y equals sine x over cos x. Of course, this looks like a fraction, and because it looks like a fraction, we're going to apply the quotient rule of differentiation. So let's go ahead and do that. All right? So we say that y equals sine x over cos x. So we can say that let that be equal to u over v. So what this basically means is that if u is equal to sine x, then it means that du by dx is equal to cos x. Similarly, if v is equal to cos x, then dv by dx is equal to minus sine x. Now, according to the quotient rule of differentiation, we can say that dy by dx is equal to v du by dx minus u dv by dx all over v squared, right? So let's see what that is going to give us. So now we have dy by dx is equal to, so we have v of course is actually equal to cos x, right? So we're going to have cos x. So this is going to give us cos x times du by dx, which of course is cos x. Then we have minus u, which is sine x, times dv by dx, which is minus sine x. And this is all over v squared, which of course is cos x squared. So looking at the numerator, we see that dy by dx would be equal to cos x times cos x, which of course is cos squared x. Let me just clear up the rest of the screen here. Right. So dy by dx would of course be equal to cos squared x, and here we have minus sine x times minus sine x, which multiplies to give us plus sine squared x. So this is cos squared x plus sine squared x, and this is what over cos squared x. Of course, we know that from our trig identities, cos squared x plus sine squared x is equivalent to 1, and therefore this is equal to 1 over cos squared x as required. And of course, we should be able to recognize this as tan x, which of course tells us that the derivative of tan x is equal to 1 over cos squared x, right? Because of course, remember that from our trig identities, then we say that, well, sine x over cos x is equivalent to tan x. And so what we basically just did was to find the derivative of tan x by treating it as a quotient of sine x and cos x. All right, so that was part B of the question. Let's look at part C. Part C says the equation of a curve is given by y equals 5x squared minus 7 all to the power of 4. Determine the equation of the gradient of the curve. In other words, they want us to find dy by dx, right? So let's proceed to doing that. So what we have is this. So we'll just clear this up a little bit. So what we have here is So what we have here is looking like a composite function. And so we have y equals bracket 5x squared minus 7 to the power of 4. So because it looks like a composite function, we're going to have to apply the chain rule. So we'll do it two ways. We can say, for instance, let u be equal to 5x squared minus 7, and this therefore means that y is equal to u to the power of 4. Now, if u is equal to 5x squared minus 7, then what this basically means is that du by dx is equal to 10x, all right? And similarly, if y equals u to the power of 4, then this further implies that dy by du is equal to 4u cubed, right? So dy by du equals 4u times 4u cubed. But of course, because u was originally given in terms of x, we can say that dy by du is equal to 4 bracket 5x squared minus 7 cubed. And having done that, now we can go and say, by according to the chain rule, so according to the chain rule, dy by dx is equal to dy by du times du by dx. And so therefore, dy by dx is equal to dy by du, which is 4 bracket 5x squared minus 7 cubed times du by dx, which of course is times 10x. And so this gives us 40x bracket 5x squared minus 7 all to the power of 3. And this right here is the gradient, or the gradient of the curve, or the equation of the gradient of the curve, which is also referred to as the gradient function of the curve. All right. So we managed to use a chain rule, but of course, I mean, there is, well, a slightly quicker version of the chain rule, and we'll just do it using that, which essentially amounts to the same thing, but it doesn't actually involve us writing down u equals that, then find du by dx, writing y equals that, find dy by du, and then putting them together. We can actually do it in a few shorter steps. So let's write it down. So the same problem, y equals 5x squared minus 7 to the power of 4. So we can see that y equals 5x squared minus 7 to the power of 4. Right, so we do recognize that this is a composite function, and we'll apply the chain rule, but a shorter way. So this is what we do. We say that dy by dx is equal to, now firstly, we treat it like a regular derivative, where we're just going to bring the power down, multiply by it, and then reduce the power by 1. So the 4 comes down, goes in front of the brackets, back the 5x squared minus 7 inside the brackets, the power gets reduced by 1. Now, because it's a composite function, we have to basically multiply by the derivative of what is inside the brackets. So we have to multiply by the derivative of 5x squared minus 7. And so continuing, what this gives us is 4 bracket 5x squared minus 7 cubed times 10x, which gives us the same result we got earlier, which is 40x bracket 5x squared minus 7 all to the power of 3. And that right there is the gradient function of the curve y equals 5x squared minus 7 to the power of 4. And this would allow us to find the gradient of any point on the curve by substituting the x-coordinate into the gradient function. So this is the end of part C of the question, and the end of question 4 from CSEC AdMaths 2024.